In this lecture, we'll explore small connectors, and essentially these are nails and screws. We will look at nails, we will look at screws and how they're used in buildings. We'll look at the capacity of type 1 nail and screw connections, type 2 nail and screw connections, and look at nail plates at the very end. So first up, some pictures of nailed and screwed connections. Nails can be used in quite large structures. In order to carry large forces, we need plenty of nails, tens of nails, and in some cases, hundreds of nails. In the left-hand photo is some connections between quite large members using plates that have got about 40 nails on each side of that element. On the right-hand side of this slide, you can see a photograph of a domestic connection where just 4 nails will carry the loads required. Likewise with screws. They can be used on large structures where a large number of screws are going to be used, or on small structures where, again, smaller numbers of screws are going to be used. So, small connections, nails. Nails are frequently gun-driven. They can be very quickly and cheaply, economically installed. Screws can be driven by machines as well, and that lessens the cost of their installation, but their installation costs are still a little bit more than nail costs. In terms of geometry, we can use screws and nails to fasten wood to wood, or we can use screws and nails to fasten steel plates to pieces of timber. Connection capacity. Type 1 connections are where the nail or screw carries the load in shear. So here I have a screw that I can pass into one piece of timber, and if it goes into the other piece of timber and loads are applied, that screw shank is carrying the loads in shear across that shear interface. So that's a type 1 connection. A type 2 connection would be this one here, where I'm pulling the upper one off, and that is putting the screw into tension. And screws have about 3 times the capacity in a type 2 connection to the same size nail. So type 1 capacity of small connections. This slide details the capacity of a type 1 nail or screw connection. And you can see again the phi factor and the K1 factor. Please note though that unlike members, we draw the K1 and the phi factors from a slightly different part of the standard. There's a different table for the capacity factors for connections and a different column in the K1 table for connections. Their values are a little bit different to the member capacity factor and K1 factor. Then there's a grain orientation factor, whether the screw penetrates the side grain of the member or into the end grain of the member. So for nails and screws, they both have a K13 factor, and it's simply a case of detailing whether the screw goes into the side grain or whether the nail or screw goes into the end grain. The K14 factor relates to the number of shear planes across the connection. So here I'm using 2 pieces of timber and there is 1 shear plane. If I'm using 3 pieces of timber, I will create 2 shear planes. And it's importantly the number of shear planes across the shaft of a single fastener that we're counting. The K16 factor relates to the head fixity factor. When a screw or nail is driven, the head is going to sit flush with the top member. If the top member is a piece of wood, there's not a lot of fixity with the head of the fastener. However, if the top member is a thick steel plate, there can be quite a lot of fixity at the top of the fastener that improves the strength of the connection a little. K17 factor relates to the numbers of rows of fasteners in a particular connection. A row of fasteners is defined as being perpendicular to the direction of force. So if this is a tension member, a row of fasteners will be in a line like this. So that if this is a tension member and I've got 4 rows of fasteners, those 4 rows of fasteners will be 1, 2, 3 and 4 rows of fasteners. Okay, the capacity of the single connector in shear, be it a nail or screw, is given in a table that looks like the one that's on the screen at the moment. And it's a function of the joint strength group of the timber. So we look up from the species of timber, what is the joint strength group of the timber, and the diameter of the fastener. The larger the diameter, the larger the capacity of the fastener, because the more shear capacity it's got to carry across the shear interface. Likewise, the higher the density of the timber, the higher the capacity of the connection as well. So QK, the capacity of a single fastener across a single shear plane, is given by a table that looks very similar to that. And screws and nails have tables that are very, very similar. The type 2 connection has a different form. So this is the capacity of a type 2 connection. We've got a 5-factor, no K1 factor. It's the first equation that I've put up that doesn't have a K1 factor. The capacity of a connection in withdrawal doesn't appear to be a function of the duration of load. It's simply a function of the grip between that fastener and the piece of timber that it is being pulled out of. It is a function of LP. LP is the depth of penetration. The further it goes into the innermost piece of timber, the higher the withdrawal resistance or the tension that it can mobilise in that particular fastener. And of course it's related to the number of fasteners N. QK is given by an equation that is very similar to the one we've met already. Down the left-hand column we have the joint strength group, and across the top we've got the diameters of the fasteners. The depth of penetration is very, very important, so that the longer the fastener and the further it penetrates down into the member, the better the resistance. Nowadays, we can get some quite long screws, and these types of screws are used for joining elements to quite deep cross-laminated timber or glue-lam members, and can get very substantial type 2 capacities. The spacing of nails and screws is limited as well by the standard, and with much tighter controls over spacing across the grain compared with the spacings along the grain. So along the grain we've got to have the fasteners further apart to prevent them from splitting the timber along the grain, along the length of the member parallel to the grain. Finally, nail plate connections can be used. A nail plate connector is a metal plate that's been bent so that there are a number of sharp-toothed nails that can be pressed into the timber. So this, using a nail plate connector, a manufacturer can simultaneously drive 20 or 30 nails into the timber and give a very strong type 1 connection. In summary, nails and screws used in large numbers can be used to transfer quite substantial loads in structural connections. The type 2 connection, a screw has a much higher capacity than a nail, but in a type 1 connection they both have very comparable capacities. The capacity of the connection is a function of the diameter and the length of the fastener, but also the strength of the wood as measured by the joint strength group. And by detailing a connection properly, we can be sure that that connection is going to perform for a large number of years without splitting.